तो थोड़ा आसान है। हाँ, ठीक है ना। इधर से।
Hello everyone, welcome back to our live discussion. Today our topic of discussion is stepper motor and I will welcome Mr. Suresh Dwivedi ji for this discussion. So my first question is, what are the key parameters you consider when selecting a stepper motor for a product?
Yeah. Yeah. When selecting a stepper motor for the product, several key parameters must be considered to ensure optimal performance, reliability, and the efficiency. For example, first consider the torque requirement. It is very essential parameter. Torque requirement should be done. So in this case, the motor must provide sufficient torque to drive the load without missing step. This includes both holding torque when the motor is stationary but the energized, and the another is the running torque while the motor is in the motion. It's essential to calculate the total load and include the safety margin. And the next parameter is the step angle and the resolution. The step angle, commonly 1.8 degree, 0.9 degree, etc., determines the precision of the movement. A smaller step angle provides finer positioning. Applications requiring high accuracy, such as robotics or 3D printing, benefits from the smaller step angles or the micro stepping. Next parameter is voltage and current rating. It is also very important. In this case, these defines the motor's electrical requirement and must match the motor driver's capabilities. Choosing a motor with the appropriate current rating is very important to avoid the overheating under performance. So current and voltage is very important. Next parameter which is important is the speed requirement. The motor must operate efficiently within the desired speed range. Stepper motors lose torque at the high speed, so the torque speed curve of the motor should be checked to match the application needs. Next parameter which we have to consider is the drive time. Choose between the unipolar and the bipolar motors. Bipolar motors generally offers better torque performance, while the unipolar motors are the simpler to drive. Another parameter is size and the mounting. The physical dimensions, NEMA size, shaft diameter, etc., should fit within the product's mechanical design and the mounting configuration. And the next and the last parameter which we have to consider is the environmental conditions. Consider the operating temperature, humidity, and the vibration levels to ensure the motor's durability in the product environment. So these parameters, you can select the stepper motor that meets the mechanical, electrical, and the environmental requirement of the product design.
Okay, so how does step angle affect the positioning accuracy in a design?
Yeah, actually, the step angle of the stepper motor directly affect the positioning accuracy and the resolution of the motion control system. Step angle refers to the angular movement the motor shaft makes with the each step signal. Common step angles include 1.8 degree, normally known as 2 steps per revolution, and the 0.9 degree, normally 400 steps per revolution, though finer revolution are possible using the micro stepping. So, a smaller step angle means more steps are required to complete one full revolution. Allow for the finger control, finer control, and the higher positioning accuracy. For instance, with a 1.8 degree step angle, each step moves the shaft 1.8 degree, whereas the 0.9 degree motor moves only 0.9 per step. So, effectively doubling the precision. It's particularly important in the application such as 3D printing, CNC machines, and the camera positioning systems, where even light inaccuracies can affect the performance. However, using a motor with a smaller step angle may also require more complex drivers and can slightly reduce torque at the higher step rates. So, additionally, micro stepping driver can further divide each steps into the smaller increment, for example, 1 upon 8 or 1 upon 16, significantly improving the smoothness and the positioning of resolution without changing the motor itself. So, that said, it's important to note that the stepper motor operates in open loop control, meaning there is no feedback to correct errors unless encoders or sensors are added. So, while a smaller step angle improves theoretical accuracy, factors like load, inertia, resonance, and the missed steps under the high load can still impact real-world precision. So, in brief, we may say that a smaller step angle enhances positioning accuracy and the smoothness, but must be balanced with the torque, driver capabilities, and the overall system requirements for the reliable operation.
Okay. So what is the role of motors holding torque in system design?
Yeah. Can you repeat the question again, please?
Yes. What is the role of motors holding torque in system design?
Yeah. Actually, when we are talking about the holding torque of the motor, actually it is the maximum torque it can exert to hold its position when it is powered but not rotating. In system design, holding torque plays a crucial role, especially in the application where precise positioning and the resistance to the external forces are needed. For example, in CNC machines, 3D printing printers are the robotic arms. Motor, motors must hold their position accurately when stationary. If the holding torque is too low or any other external forces are applicable, like weight of the load or the vibration, can cause the motor shaft to slip or rotate, leading to error or system failure. So, holding torque is essential, especially important for the stepper motors, which are commonly used in the precise motion control. So, these motors rely on the holding torque to maintain their position between the steps. Without adequate holding torque, they can lose steps, causing misalignment or the incorrect movement. So it is very important in case of vertical application like lifting mechanism or the elevator, holding torque prevent the load from the falling when the motor is not rotating. So it ensures the motor can resist gravitational forces and maintain safety. When designing a system, the holding torque must be higher than the any static load the motor must resist. A margin of the safety is also essential to account for the variation in the load, temperature, or wear over time. So when summarized, we can say that the holding torque is very critical for maintaining accurate position when stopped, resisting external forces or gravity, ensuring safety and the system reliability, preventing slippage or the step losses. So properly selecting a motor with the adequate holding torque ensures smooth, accurate, and the sharp operation of the motion-based systems.
Okay,
Yeah,
so how do you match a stepper motor with a gearbox or lead screw in a motion system?
yeah. Actually, when we are talking about the matching a stepper motor with the gearbox or the lead screw, it involves ensuring that the motor provides enough torque and the speed to move the load accurately and efficiently. For example, first, understand the load requirement. First, start by identifying how much force is needed to move the load and how fast it needs to move. For linear systems, using lead screw determine the linear forces in Newton and the required travel speed. Lead screw are the gearbox ratio. And first we should know what is the lead screw. Actually, lead screw converts rotatory motion to the linear motion. The lead means distance moved per revolution directly affects the speed and the force. So a fine pitch lead screw gives high force but the low speed. A coarse pitch screw gives higher speed but the less forces. So a gearbox reduces the speed and increases the torque. Gear ratios like 5:1 or 10:1 multiply torque by the factor but reduce the output P. So we should calculate actually torque needs. Use a force and the mechanical setup to estimate the torque required at the motor shaft. Then the match this with the motor's torque curve. If the motor alone can not provide enough torque, use a gearbox to multiply. Next parameter which we have to consider is consider the speed and the resolution. It is also very important. Higher gear ratios are fine lead screw give better positioning accuracy, more steps per unit of the motion, but reduce the speed. Match this to your system's speed and the precision needs. So, next parameter, factors in the efficiency. Actually, gearbox and the lead screws are not the 100% effective, efficient. So, account per losses typically 20 to 30% when estimating the required motor torque. So test and adjust after reselecting. Test the system under the real condition. If the performance is not as expected, adjust the gear ratio or the screw pitch accordingly. So, in short, a balanced torque speed and the accuracy while considering the mechanical losses to ensure proper match.
Okay, so how do backlash and mechanical play affect stepper motor performance, and how do you minimize them?
Yeah. Just repeat the question again, please.
Yes, yes. How do backlash and mechanical play affect the stepper motor performance, and how do you minimize both of them?
Yeah. Very good question. Actually, backlash and the mechanical play refer to the small gap or the looseness and mechanical components like gears, lead screws, or coupling. These issues can significantly affect stepper motor performance, especially in the system requiring precise motion. That case. So, effect on the performances. First, loss of the position accuracy. When the motor the changes direction, backlash causes a delay before movement resumes. Since the motor must take up the stack first, so this results in the missed steps or the positioning error. Another is the vibration and noise. Mechanical play can cause sudden shift during the motion, leading to the vibration. So increased noise and the mechanical screws. Inconsistent motion. Backlash can lead to erratic movement, especially during the small or the rigid position changes, making it difficult to achieve a smooth motion. So, reduced repeatability in the application like 3D RCNG, matching backlash can prevent the system from returning to the exact same position after the cycles. Now the question arises how to minimize the how to minimize them. So for minimizing, first of all, use anti-backlash nuts and the screws. It lead screw systems, anti-backlash nuts apply consistent tension to eliminate the gap between the threads. Next parameter to minimize is the preloaded bearings. These removes play by applying a slight opposing forces, keeping components tightly engaged. Next parameter is the zero backlash coupling. What is the zero backlash coupling? Actually, use high precision coupling that don't flex under load. Helical or the disc coupling are the very good option. So we should apply these. High quality gears are the belt. Use timing belt or precision cut gears with the tight tolerance to reduce the gear backlash. And the last is the software compensation. Some motion controllers allows backlash compensation, adjusting movement to account for the non-mechanical play. So, in brief, we can say that the backlash and the mechanical play reduce the precision and the repeatability in the stepper motor systems, minimizing them through the better mechanical design and the quality component is the key to ensuring accurate, smooth, and the reliable motion. Yeah.
Okay. Okay. So, how do thermal effect in the motor influence the mechanical enclosure or mounting design?
Yeah. Actually, when we are talking about the thermal effects, so it affects the stepper motors, can significantly influence the mechanical enclosure and the mounting design, especially in the system where the motor runs continuously or under heavy load. So now the question arises, why it matters? When stepper motor generates here heat when the stepper motor generates heat during the operation due to electrical resistance and the magnetic losses. If this heat is not properly managed, it can lead to first overheating, second thermal expansion, and third heat. In case of overheating, it reduces the motor's efficiency and the lifespan. In case of thermal expansion, which may affect alignment or the cause mechanical stress. And when talking about the heat transfer, so it can damage nearby components like plastics, sensors, or the electronic circuits which is connected nearby. So another parameter is the design consideration. To avoid the thermal effects, we have to consider the designing actually. So first we consider ventilation and the airflow. When it is adequate, sufficient, so it ensures the enclosure has adequate ventilation, use vents, fans, or allow the natural airflow to keep dissipate heat from the motor. And mounting material is also very important. Use thermally conductive materials like aluminum for the motor mounts to act as the heat sink and draw heat away from the motor. And the next is the designing part is the motor space. When you are designing, keep space between the motors and the heat sensitive components. Avoid enclosing the motor in a tight or the sealed box without ventilation. Thermal isolation. It is also very important. If nearby parts are sensitive to heat, use insulation or the thermal barrier to reduce heat transfer from the motor. And the next parameter is the heat sink or the cooling devices. When you are designing, you have to consider these things. For the high performance system, consider attaching external heat sink or even forced cooling fan or the liquid cooling to the motor mount. Another designing parameter which we have to consider is the thermal expansion allowance. Accurate for the small dimensional changes due to the motor heating in high precision system. Ensure that the motor mounting does not create stress as the motor expands. So when we summarize, we can say that the thermal effect influences both components, protection, and the long-term reliability. Proper thermal design around the motor ensures stable and the performance to prevent the failure due to the heat. Yeah,
Okay, so how do you choose the appropriate driver circuit for a stepper motor?
yeah. Actually, when we are choosing the right driver circuit to your stepper motor, very it is very essential for the ensuring smooth, accurate, and the efficient operation. The driver controls how power is delivered to the motor coils, so it must match both the motor's electrical requirement and the application's performance need. Now consider the key factors to consider. So first, what we have to choose the type of motor. The motor type, identify whether your motor is unipolar or the bipolar. Bipolar motors need a H-bridge based driver, while the unipolar motor can work with a simpler circuit. Okay. We have to consider which type of motor you are using. Next key factor to consider is the current rating. Actually, we have to check the motor's rated current per phase. Choose a driver that can apply at least then much current. Ideally with some headrooms, if the motor supplies less current, the motor may underperform. Another key parameter is the voltage compatibility. Ensure the driver supports the supply voltage you intend to use. Higher voltage often allows better performance, faster acceleration, but the driver must be rated it out. Next parameter which we have to consider is the micro stepping support. Actually, micro stepping improves some smoother and the resolutions. Choose a driver that supports the required micro step level, for example, full, half, 1/4, 1/8, and 1/16. This is the important in applications needing precision or the wide operation. Next considering parameter is the control interference. Match the driver's input with your control system, for example, step direction signal from the Arduino, Raspberry Pi, or the PLC, etc. Some drivers also support serial SPI or the I2C interface. Another is the protection features. Actually, good driver includes over temperature, over current, and under voltage protection to safeguard both the motor and the circuit. Next considering parameter is the size and cooling. It is playing a very crucial role. So for compact designs, choose a driver module that fits your enclosure and provides sufficient cooling via heat sink or the fan, whatever the need. Now, so we can summarize that match the driver to your motor type, voltage, current rating, while also considering micro stepping, control interference, and protection features to ensure the optimal performance and the reliability of the motor.
Okay, so when would you prefer closed loop control with a stepper motor in your application?
Just actually, in this case, can you repeat the question, please?
Yes, yes. When would you prefer closed loop control with a stepper motor in your application?
Yeah. Actually, in the case of closed loop system, when we are talking about the closed loop system, uh, a stepper motor is the preferred when the higher precision, reliability, and the dynamic performance are required. Beyond that, open loop system can offer. Unlike traditional open loop system, which operates without feedback, closed loop systems are sensor, usually encoders, to continuously monitor position or the speed and correct any deviation in the real time. So you would prefer closed loop control to the following situation. First situation is the actually high accuracy and the reliability needs. When missing steps can result in costly errors such as in CNC machines, 3D printing, or medical devices, closed loop systems help ensure exact positioning. And the next is the variable load condition. In application where the load on the motor changes unpredictably, such as robotic car or conveyor belt, handling varying weights, closed loop feedback ensures the motor adjusts torque accordingly. So, torque optimization. Closed loop system can use the minimum current necessary to maintain the performance, reducing heat and power consumption, especially useful in the laboratory powered or thermally sensitive environment. Next parameter is the faster acceleration and the deceleration. Because the real-time feedback, the system can safely run at high speed without fear of the step loss, improving cycle time in applications like pick and place machines. Now, next is the stall detection and the recovery. Actually, closed loop stepper system can directly stall or obstruct and take corrective actions, reducing downtime. Another parameter is the reduced resonance and the smoother motion. Actually, feedback allows the system to actively dampen oscillations, making it better suited for the applications requiring smooth motions. So, in summary, we can say that when we are using the closed loop stepper motor, it controls with precision, adaptability, efficiency, or the fault tolerance in critical to your motion control application. Yeah.
Okay, so this is my last question for the session. In a compact product, how do you handle vibrations or noise generated by the stepper motor?
Yeah. Actually, in compact products, vibration and the noise from the stepper motors can be problematic, especially when space is limited and the noise-sensitive components are nearby. To handle these issues effectively, several strategies can be employed. The first strategy is the micro-stepping. One of the most effective methods is using a micro-stepping, which divides each full step into smaller increments. This results in the smoother motion and significantly reduces vibration and the audible noise. And next strategy is the current control and the damping. Using a current control divider with the active damping or the anti-resonance features help suppress mechanical resonances and the stabilize motor's operation. Modern stepper driver often have built-in algorithm for the smoother motion. Another strategy is the proper mounting and the isolation. Mount the stepper motor on the vibration damping material such as rubber grommet, silicon pads, or any foam. This prevents the vibration from being transmitted to the rest of the compact enclosure. Next strategy is the lower acceleration and deceleration. Sudden changes in the speed can increase vibration. Tuning the motion profile with the gentle acceleration and the deceleration curve using S-curve profiles can reduce the mechanical stress and the vibration. Next strategy is the mechanical design adjustment. Add mass to the frame or the use stiff balanced components to absorb or reduce the effect of the vibration. Short, well-supported shaft and the tightly coupled assemblies minimize vibration amplification. Closed loop stepper motor. Another that is the closed loop stepper motors. These motors actually adjust performance in the real time and can dampen oscillations more effectively, further reducing noise and the vibration. Last strategy is the motor sizing. We should use the proper motor sizing motor. Oversized or the undersized motors may operate inefficient, increasing noise. So choosing the correct size motor for the load helps maintain a smooth performance. So when we summarize all the things, we can say that reducing stepper motor noise and the vibration is compact products require a combination of the electrical, mechanical, and the control techniques to ensure the quiet and the stable operation.
Okay. So this brings us to the end of the session. And if you have any question, kindly post them in the comment section. We'll get back to you in the next session. Thank you for your time.
Thank you.